Hi guys, let's take a look at this section. This section is full of the applications of derivatives. Now, the main theme is this. If you are given a function in a problem and the derivative of f is interpreted as the rate of change. So in other words, if the problem involves the rate of change, so what does that exactly mean? That means how fast something is changing. That means the rate of change. The first type of application is the one-dimensional motion. So which means we are talking about the movement on a straight line. That's one-dimensional. Two-dimensional is on the plane. Three-dimensional is in our space, the regular space that you're in. So we won't be able to talk about two-dimensional or three-dimensional until calculus 3. So now the first thing that we want to mention is a few points to make for the one-dimensional motion. One, the average velocity is the change in position. By the way, we have to introduce this s of t. So from now on, let's say s of t means the position function, where you are at, in other words. So to find the average velocity, you use the change in position divided by the amount of time that elapsed, right? So therefore, change in position divided by change of t, change of time. The second point to make is the derivative of position function. That means how fast you are changing your position. That's the instantaneous velocity. That's the velocity. So which is the rate of change of displacement. Put it in another words, like in math, we say velocity is the derivative of the position function. Now the speed is different from velocity. Speed doesn't have direction. Velocity, you have direction. So the speed is absolute value of the velocity. So velocity, if you're talking about positive velocity, then that means you are moving forward. If you have a negative velocity, that means you're moving backward. For speed, it's always going to be non-negative. The third point is to talk about the rate of change of velocity. That means how fast the velocity is changing. That's acceleration. Because, and this is the notation a of t. So acceleration is how fast velocity is changing. That means the derivative of v, the derivative of velocity. Because the velocity is the derivative of position, as a consequence, the acceleration is actually the second derivative of the position function. Again, velocity and acceleration, they're both they have direction. If acceleration is greater than 0, that means your velocity, the change in velocity is getting is greater than 0. That means your velocity is actually picking up the speed. When the acceleration is less than 0, that's just the other way around. The velocity is decreasing. When the acceleration is equal to 0, that means you don't have any rate of change in the velocity. That means your velocity is constant because there's no change in velocity, right? Okay, the first problem we're gonna look at is the first problem we are going to look at is, let's take a look at this. So you are given the position function of a police car. So this curve represents the position of a police car. When the position is greater than 0, that means you are the police car is to the east of the starting point. When s is less than 0, that means to the west, because they are a straight line. The first question here, we want to describe the position of the patrol car during the first 3.5 hours. So there were 3.5 hours here, and we want to describe what's going on there, right? Okay, so therefore I'm gonna try to describe that. I'm gonna draw a straight line to represent where the car is, and I want to pick the starting point 0. That's where the car is at. I mean the initial position. Now let's read the graph. When at the beginning right here, so that's when time is 0, the position is 0, so that's where we are at, position is 0. 0.5 hours later, the car is at 20 miles. Because it's greater than 0, I know it's going to be to the east, so I'm going to write, hey, the first half an hour the car actually goes from here, so go to the east, right? And then if you can see that 1 hour later the car is at 60 miles from to the east, and then 1.5 hours later the car is 80 miles to the east. So with that, I know, hey, I'm gonna move to here, and this is 80 to the east, and this is actually time is equal to 0.5 when it is, say, 20, and when it is 60 the time is actually 1 hour, right? And the time is 1.5 hours. That's where the 80 is. Let's continue to look at the graph. So from 1.5 hour to 2 hours, this line is flat. The curve is flat. In other words, the car is always 80 miles to the east. What does that mean? That means the car is in state, doesn't move for half an hour. So in other words, I am gonna change the color here. So for the half an hour it stays here, right? So t is 2.0. the position is still the same. Now let's continue to read. After 2 hours the position decreased from 80 to 60 and so on and so forth, and then seems like this is about 3.25. so about 3.25 hours later it comes back to the position is 0. So because we are seeing that position is decreasing, that means the car is actually traveling backwards, and then it hits the original starting point when the time is 3.25 hours. So here the time is actually 3.25 hours, and then after from 3.25 hours to 3.5 hours, the car actually is, the S is less than 0. That means the car is moving towards west. So that's why we continue to move towards west, and it's about after 0.25 hour when time is 3.5, this is actually negative 20. So basically that's what we have. What we see from the graph means the police car starts from somewhere, drive forward for 1.5 hours, and stay at one place for half an hour, and then drive backwards past the original starting point and move further to the west and then stop. That's what's happening. So I spent a good amount of time explaining the graph. The next thing is, let's graph the instantaneous velocity of the patrol car. So hopefully you can now recognize how do you find the velocity. It's just derivative of st, right? So we did that back in last section. I'm gonna just repeat that. So here we wanna graph the velocity on this graph, basically the derivative of this curve, the function we are given. You may want to pause for a moment so that you can think about it before you continue to watch this little video. So pause that and then check with your answer with mine, compare your answer with mine, and to see where how well you do. Okay, now I'm gonna continue. First of all, if you think of the derivative as the slope of any points on the curve. So I will begin like this. Here, the slope at the beginning seems like this is pretty flat, right? So therefore, my derivative at this point will be 0. And then at this point, it seems like about maybe the tangent line is about 45 degree, so which is about 1. I'm gonna draw, hey, at this point this is about 1, so this is 10, actually it's pretty low here, this is 1. Okay, let me erase that and put a dot here at 1. Okay, and at this point, oh, by the way, I have to take it back because I cannot say it's 1. They're on different scale. Here this is each grid is 10, and here each one is just 0.5. I'm not gonna say it's 1, so I'm gonna redo a little algebra here. It seems to me this is about vertical is about 15, 14 and 15ish. Let's pick a nice number, 15, and the run is about let me just use 0.5, just a good approximation already. So actually this is about 30, right? So 30 miles per hour, in other words, at that point it's about 30 miles per hour. So I'm gonna erase that. Don't let that distract us. So therefore at that point, at this point, it's about 30 miles per hour here. And then continue to grow. Say at some point here this is pretty straight line. It looks to me they're very straight line. When you have a straight line, that means your position is straight line. That means the derivative, the slope of tangent is pretty much coincide with this line. So therefore the velocity is actually constant. The derivative is the same everywhere on this segment. So if you make a rough estimate here, so 1, 2, 3, 4, the 40 change on top and 0.5 change on the bottom. So 40 over 0.5, which is 80 miles per hour. So during this period, I'm gonna say it's about 80 miles per hour, and it's about the same everywhere. So therefore I'm gonna draw this graph. By the way, I'm gonna erase those so that it doesn't distract you. So 80 miles per hour, okay. And then after, on this particular segment here, so from this segment it slows down, and then this in this area the slope is 0. That means the velocity is 0. So just make a kind of rough estimate. So from here to here the slope is 0. That means velocity is 0. Now let's continue to look at the graph. Here, just picture in your mind, in your head. So the slope here is quite kind of somewhat flat, right? And then somewhere from here to here looks like pretty straight line. So similar reason for that, because it looks like straight line, I would say the velocity is pretty constant. And then let's make a guess here. So 1, 2, 3, 4, 4 change, and this is 0.5 hour, so about negative 80, right? So negative 80. I'm gonna erase those. Okay, so that means at this, from here to here it's negative 80. I need some space, but that's what's happening here. And of course the speed, the slope is getting steeper. That's why this is going down, and here this is flat because the speed is constant. And then so here this is still quite steep, right? And here at the end I see a little curvy. It's, if I zoom in, it looks like this. It looks like this. So probably here this is considered as a horizontal tangent line. That means the car stops. So I'm gonna erase that again, and this is continue to quite flat. Not until now. the curve becomes, oops, 0. I'm gonna touch 0 because its speed is 0. So this is pretty much the velocity graph that I would draw for this particular graph.